All right, so unfortunately I wasn't able to hold the Zoom meeting today, so this is July 13th, and my internet is acting up, so I'm going to have to figure out what's going on there, but I wanted to at least answer the questions that you all just posted on the discussion boards. So this isn't quite as perfect, I guess, as having a Zoom meeting, but at least I can work out some of the problems that you posted questions about. So one of the questions was 3.1 number 26. So it was this limit as x approaches infinity. Limit as x approaches infinity of negative e to the negative x minus 2 plus 1. So the question was, how to calculate this limit. And my answer is, if you were to take a look at the graph of the function, it would be very obvious what the limit is. So one way to find this limit would be graph the function and just kind of see what's going on. Another thing you could do is you could just plug in bigger and bigger values for x and see what's happening. And that one is kind of easy to imagine. So if you imagine plugging in some, I'm sorry, was it an e to the negative x minus 2? Is that? So 26. No, it's just negative e to the x to the positive x minus 2. My apologies. So it's a positive x minus 2. Anyway, so yeah, so if you imagine plugging in a really big value for x, like 10,000, right? 10,000, or maybe if we plug in 10,002, that way if we subtract 2, we still get 10,000, right? But e to the 10,000 power is some really big number. But of course you're making it negative, so it's going to be big in the negative direction. And you're going to add 1 to that, but it's not really going to matter. I mean, if you're looking at e to the 10,000, right? Adding 1's not really going to change that answer very much. So, so it's pretty clear, and that's if you plug in 10,000. If you plug in a million, you're going to get something even bigger, but of course in the negative direction, right? So, normally exponential functions have a horizontal asymptote at 0, right? But this has been shifted up 1, so you're going to have a horizontal asymptote at 1. Okay, and then usually they go up like this, okay, but this thing's been flipped over, so it's actually going to go down like that. Okay, so that's a really rough sketch of the graph. But at least you can see, looking at this graph, that as x gets really large, f of x is going to get really small, or really big, I guess, but in the negative direction. So this limit, the limit as x approaches infinity here, is going to be negative infinity. Now, if you were looking for the limit as x approaches negative infinity, then you would say the limit is 1, right? Because f of x is getting closer and closer to 1 as x approaches negative infinity. But as x approaches positive infinity, right, you're approaching negative infinity. So that was 3.1 number 26. And then another question was just to do a graphing problem in more detail. So this is sort of a quick sketch, but if we wanted to graph something in detail, like the question was number 11 from 3.1. So on 3.1 number 11, the function is f of x equals 2/3 to the x power plus 3. So to graph these functions, just remember they have a horizontal asymptote. They have a horizontal asymptote at y equals 0, usually, but this one's been shifted up 3, right? So really our horizontal asymptote is going to be at 3. And then they also usually go through the points 0, 1, 1 base, in this case the base is 2/3, and then negative 1, 1 over base. So if the base is 2/3, then 1 over the base is 3/2, right? It's the reciprocal. This is what f of x equals 2/3 to the x would go through, but again, we're adding 3. That means all of these points need to be shifted up 3. 3 and 2/3, and then negative 1. 3/2 is 1.5, so if you shift it up 3, you're going to be at 4.5. Okay, so we can get a pretty good picture of this thing now, right? So, so we've got this asymptote at 3. And then we know that it goes through 0, 4. 1, 3 2/3, so 3 2/3, maybe right about there. And then negative 1, 4 1/2, right? So 1, 2, 3, 4 1/2 is right about there. So this function is a decreasing function. Okay, so it's going to look something like that. So that's how these things go. So that's it, I think, for 3.1. I think that's all the questions you had about 3.1. So let's move on to 3.2. In 3.2, we had questions about number 17, 27, 53, and 55. So let's take each of those. So looking at number 17, it says evaluate each expression without a calculator. It's 3 to the log base 3 of 5. Well, that's easy, right? We had a property of logarithms that said some number raised to the power of a logarithm of the same base. The exponent or the base and the logarithm just cancel each other, right? So this thing is just going to be 5, right? The 3 and the log base 3 will cancel. You're just going to be left with 5, right? So you'd say 3 to the log base 3 of 5 is equal to 5, and that's all there is to it. Okay, so that's number 17. Let's look at 27. So 27 says graph the function. We have a logarithmic function. Okay, let's do it. So we have f of x equals log base 1/5 of negative x. So let's just remind ourselves. A logarithm usually looks like this. But this would be f of x equals, log base 2 of x or something like that. What's different about this one is that the base of our logarithm is 1/5, so it's not going to do this same thing. What would it do? It's going to go kind of in the other direction, like this. Okay, that would be log base 1/5 of x. But then the other thing that's different is that this is log base 1/5 of negative x. So actually this whole thing is going to be shifted. It's going to be reflected across the y-axis. So this is sort of going to be the final answer, I think. Is going to look something like this one over here. But if we wanted to graph it a little bit more carefully, what we would say is, first of all, this thing has a vertical asymptote at x equals 0. Unless it's been shifted left or right somehow. This one hasn't been shifted left or right, so the vertical asymptote is still at 0. And then it usually goes through, now logarithms go through the same points as their exponential counterparts, but with the coordinates switched. So instead of going through 0, 1, it's going to go through 1, 0. And instead of going through one base, it's going to go through base 1. And instead of going through negative 1, 1 over base, it's going to go through 1 over base, negative 1. Now this is without applying the transformation though. We have a transformation here where we have to multiply all of our x coordinates by negative 1. So actually this is going to go through negative 1, 0, negative 1/5, 1, and negative 5, negative 1. Okay, so let's plot those points. We've got this vertical asymptote at 0. Then we're going to go through negative 1, 0, negative 1/5, 1, and then negative 5, negative 1. And so that's going to look something like this, kind of like we suspected it would look. Okay. If you miss your point, just make the point bigger. Now, that's 27. I'm going to pause the video so I can return this phone call that you just heard me get. You won't feel it though. And I'm back. Okay, so what's the next question on the list? So number 53. Let's take a look at 53. Okay, oh, 53 and 55. Oh yeah, so okay, so they're very similar, right? I mean, maybe I'll skip 53 and just do 55. I think if I show you 55, well, actually, then again, maybe I'll show you 53, and then you can do 55 on your own, potentially. 53 is log of 2 over x. And we're supposed to use the fact that log of x is 2. And so we're told that log of x is 2, log of y is 3, log of 2 is about 0.3, and log of 3 is about 0.48. So I'm just writing that stuff down. Okay, but we want to figure out what's log of 2 over x. Well, this is where you would use the quotient rule to say log of 2 over x is just log of 2 minus log of x. Right? You remember the quotient rule for logarithms, right? So that's what we're applying here. Log of 2 is about 0.3, and log of x is 2. 0.3 minus 2 is like negative 1.7. Right? So that would be it for 53. 55 is a little bit more involved than that. Maybe I'll do 54 in the hopes that you can do 55 on your own. But 54 is, we've got log of 2x squared y. So you're going to have to apply some product rules, some power rules, right? You're going to say this is log 2 plus log x squared plus log y. And what's log of x squared? Well, this is log 2 plus 2 log x plus log y. So to get from here to here, this first step, I'm using the product rule. And then to get from the second step to the third step, I'm applying the power rule, right? Bringing this exponent down in front. And now you can plug in, I'm not going to finish it, but now you can plug in the values for log 2, log x, and log y that you were given in the problem to figure out what the numerical value of this thing would be. So that's all I'm going to say about 53, 54, 55. And that's it for 3.2. So let's move on to 3.3. You had a lot more questions about 3.3, and I understand that. I think that there's a lot of kind of confusing stuff in 3.3. So I want to go through the list and kind of talk about how you would solve these problems. And some of them maybe I'll work out in detail, and some of them I won't. But on 3.3, one of the questions was number 17. 2 to the 1 minus x equals 3 to the 4x plus 6. I think this would be a good one for me to work out in detail. Because all of the problems are going to be more or less like this. So let's take a look. Okay. Here you have two exponentials and the bases are different. If they had the same base, then you would just take log of that base. So if this was 2 to the 1 minus x equals 2 to the 4x plus 6, well then you could just take a log base 2. And that would clear everything, right? It would just bring the exponents right down, which would be nice. But since your bases don't match, it's maybe a little bit confusing. You're like, which logarithm should I apply? But remember that you can always just take natural log or log base 10 or something. Since you're going to want to use your calculator to get a decimal approximation anyway, that's what I would do. I would just go ahead and take natural log of both sides. And now what's going to happen is that you can pull the exponent in front. So you have 1 minus x times the ln of 2 equals 4x plus 6 times the ln of 3. And then your task is to solve for x. So however you want to do that is fine. I think what I would do is distribute the logarithms. ln2 minus ln2x equals 4 ln3x plus 6 ln3. And just remember, these logarithms, they're just numbers, right? So, I mean, you just want to get your x's on one side and your numbers on the other. So I'm going to subtract the 4 ln3 times x over to the other side and get negative 4 ln3 x minus ln2 x equals, and then I'm going to move this ln2 over to the other side, so I'm going to have 6 ln3 minus ln2. right? So I subtracted this over here, and I subtracted this over there, okay? And now to finish solving for x, I mean, you could factor out an x. You would get x times negative 4 ln 3 minus ln 2 equals 6 ln 3 minus ln 2, and then divide by x, right? So you get x equals 6 ln 3 minus ln 2 over negative 4 ln 3 minus ln 2. And that's that. That's an exact answer that'll work. You can pop that into your calculator to see about how much you get. I'm not really interested in doing that. Okay, that's how you do number 17. So the moral of the story is this: to solve a logarithmic equation, you isolate a logarithm, and then you, we're dealing with exponential equations here, right? To solve an exponential equation, you isolate an exponential, and then you take a logarithm of both sides, and that's going to allow you to bring the exponent down in front. So looking at something like number 19, so on number 19, the trick is to sort of see this as something that's quadratic in form. That's maybe a little bit difficult to do, but let's write this thing down, and then I'll show you what I mean. So 19 is 9 to the x minus 6 times 3 to the x plus 8 equals 0. You want to try, if possible, we would like to get our logarithms written in terms of the same base. This exponential is base 3, this exponential is base 9, but I can always rewrite a 9 as 3 squared, right? So this is really 3 squared to the x minus 6 times 3 to the x plus 8 equals 0. 3 squared to the x, I mean, this is just 3 to the 2x power minus 6 times 3 to the x plus 8 equals 0. And now maybe you can see that this is in fact quadratic in form. It's like you've got something's, in fact, let me take it one step further and say this is 3 to the x squared, right? It's just 3 to the x squared minus 6 times 3 to the x plus 8 equals 0. So you've got something squared minus 6 times something, right? That same thing plus 8 equals 0. Well, this is just a quadratic equation. Right? It's just a quadratic equation. It's something squared minus something plus something else equals 0. So we can try to factor this. To get 8, I think negative 4 and negative 2 will work. So I'm going to do 3 to the x minus 4 times 3 to the x minus 2 equals 0. And if we were to multiply this out, we would get 3 to the x times 3 to the x. That's 3 to the x plus x, or in other words, 3 to the 2x. Right? Minus 2 3 to the x minus 4 3 to the x is a negative 6 times 3 to the x, and then plus 8. So the factorization works. So I'm not going to finish the problem, but now you would say, okay, so that means 3 to the x equals 4, or 3 to the x equals 2, and then you would finish by taking logarithm of both sides, right? So the rest is history. Okay, so that's number 19. Number 21. You asked questions about almost every single one of these, so maybe I'll go through a little more quickly on number 21. Multiply both sides of the equation by this denominator, okay, to clear the fraction. And then solve this like we solved number 17, right? Isolate an exponential, take a logarithm of both sides, right? So that's it for 21. I'm not going to work it out in detail. The rest of these are all logarithmic equations. So with a logarithmic equation, you follow the same sort of strategy, except that instead of isolating an exponential, now you're going to be isolating a logarithm. And once you've done that isolation, instead of taking a logarithm, you exponentiate. Okay? So in order to undo an exponential, you take a logarithm. In order to undo a logarithm, you exponentiate. All right? I'll be honest with you, I'm a little surprised you're asking about 23. This is a fairly simple logarithmic equation. I think I'm going to skip that one. we had to have done one similar to it in the notes, right? You just isolate, right? You isolate log of 2x plus 5 by subtracting 3 over to the other side, and then you exponentiate. This logarithm has base 10, so you would exponentiate by 10 to clear the logarithm, right? And that's all there is to that. I might want to show you one a little more interesting than that. Let's do so 23, and then the next question you had was about 29. 29 would be a good one. It would maybe be even better if we did 31 first, which you actually asked about already. So let me show you 31. That's what I'm going to show you, is how to do number 31. So for 31, we have log base 3 of 2x minus 7 minus log base 3 of 4x minus 1 equals 2. So the first thing I'm going to do before I exponentiate is I'm going to try to rewrite this as a single logarithm. And I can do that, right? Log base whatever minus log of that same base. That's just log of that base of argument divided by argument, right? This is just the quotient rule. We would say this is 2x minus 7 over 4x minus 1, right? So it's log base 3 of 2x minus 7 over 4x minus 1 equals 2. And now we exponentiate. In this case, since the base is 3, we're going to exponentiate by 3, right? Now 3 to the log base 3 cancel and leave us with 2x minus 7 over 4x minus 1. 3 squared is 9. And the rest is history, right? I'm not going to finish it, but from here you would multiply both sides of the equation by 4x minus 1 and then solve for x, right? And just be sure that you check your solutions, right? You have to check your solutions to make sure that they don't make any of the arguments negative. Okay? So with that in mind, looking back then at number 29, log base a. So what makes this one a little difficult is that you don't even know what the base is. But as we'll see in a second, it doesn't matter. So we have log base a of 5x minus 2 minus log base a of 3x plus 4 equals 0. So following the same strategy, I would rewrite this as a single logarithm, right? It's log base a of 5x minus 2 over 3x plus 4 equals 0. And now I would exponentiate by a in order to clear that logarithm. A to the log base a is going to cancel for any base a. So we're just left with 5x minus 2 over 3x plus 4 equals a to the 0 power. Well, any number to the 0 power is 1. Right? And then the rest is history. Okay. So what other questions did you have about this section? So we've done most of, we've at least briefly talked about most of these things that you had questions about. Then you had 35, or 33, 35, 37, 39, 41. Wow, you asked really almost every single odd numbered problem here. Let's look at 33. So let's at least talk about 33. It says find the time required for an investment of $10,000 to grow to $18,000 at an annual interest rate of 6% if the interest is compounded yearly, monthly, and continuously. Okay. So on 33, for part A and for part B, you're going to use P equals P naught times 1 plus R over N to the NT. That's the formula you're going to use. Same thing for part B. I can't remember if I used P or A in these locations, but it's the same formula either way. And for part C, you're going to use P equals e to the RT. Okay? So that was the main purpose of this exercise, to get you to see that, when you're compounding continuously, n goes to infinity, and so this whole thing just goes to here. Actually, I think it's P equals P naught, e to the RT. So this portion of it goes to e to the RT when n goes to infinity. Okay, so let's plug in some numbers to make sure that we can do this. If you compound yearly, then n equals 1. Your initial amount is 10,000, your final amount is 18,000, and your interest rate is 0.06. So for this top equation, we're going to say our final amount, 18,000, equals our initial amount, 10,000, times 1 plus r, 0.06, over n, which is 1, to the n, which is 1, times t, which we don't know. T is what we want to solve for. Whoops. So this is the resulting equation. In part B, you're compounding monthly, so you would say exactly the same thing, except n is 12. And then you want to solve that for t. And in part C, you'd say sort of the same thing. Your final amount is your initial amount times e to the r times t. And you solve that for t. This last one is the easiest to solve for t. But in every single case, what I would do personally is I would simplify the stuff on the inside of the parentheses. I would divide through by 10,000. So you're going to get, 1.8 equals, 1.06 to the t. And then just solve for t by taking logarithm of both sides. I would just go ahead and take the natural log. Since you're going to want to get a decimal approximation anyway, I would just take ln of both sides at that point. Same thing here, right? Divide by 10,000, do this addition, okay? And then take the natural log of both sides. On this one, you'll have the additional step that you'll need to divide by 12 after you've taken the logarithm of both sides, right? In order to finish solving for t. But that's all there is to 33. Let's look at 35. The light intensity I in lumens after at a depth of x feet in Lake Elizabeth is given by this logarithmic formula. Part A asks, find the light intensity at a depth of 30 feet. So the depth is x, right? In this equation, the depth is represented by x, right? It's at a depth of x feet. So if the depth is 30 feet, you're going to plug in 30 here and solve this equation for I. So we've got log of I over 12 equals negative 0.025 times 30. Um, 0.025 times 30 is 0.75. So we have log of I over 12 equals negative 0.75. And now this is a log base 10. Remember, when there's no base written, it's assumed to be a 10. So I'm going to exponentiate by 10. And that's going to cancel the logarithm. I over 12 equals 10 to the negative 0.75. And then I'm not even going to write that down because I know that I want to multiply my answer by 12. So I'm going to multiply, I'm just going to say times 12. You should get about 2.13. Did it say how much to round to? It didn't say how much to round to, but we would say about 2.13 feet for part A. For part B, it's asking you to do sort of the opposite. Like, at what depth is the light intensity 4 lumens? So this time they're giving you the light intensity I. So they're saying I is equal to 4. So plug in 4 for I and then solve for x, right? So that's just a linear equation. You just, you plug in 4 for I, and then you divide by 0.025, and that's all there is to it. So that's it for 35. 37, 39, 41, they're all word problems. I know we did something very similar to 37 in the notes. I have a feeling I know what's maybe throwing you off, right? So it says in 2011 the world population was 7 billion, so your initial amount is 7 billion. And then a year later, the population had grown another 90 million. So what may be throwing you off is that 90 million is not, in other words, the total population of the world is not 7.9 billion in 2012. It's 7.09 billion, right? 7.9 billion would be 7,900,000,000, right? So so if you've grown by another 90 million, then really it's 7.09 billion is your final amount, I guess you could say. So 1 plus r over n to the nt. Okay, so let's see what we've got. Sorry, I wrote down the wrong formula. So actually what we would say is this. We say P equals P naught times e to the RT. P naught is our initial amount, which was 7 billion. I'm just going to leave it. I'm just going to write it in terms of billions. And then P is our final amount, which was 7.09. If the world population increased by another 90 million, that's 0.09 billion. Okay. Times e to the r times 1, right? It only took 1 year for it to make this amount of growth. So we can solve this thing for r now if we divide both sides by 7. So e to the r equals 7.09 divided by 7. I would take the natural log of both sides now and say r equals natural log of 7.09 over 7. Okay, so that's our growth rate. You could plug that into your calculator and get a number, I guess. But we want to know what the population is going to be in 2021. So the population in 2021 is going to be the population in 2011, which was 7 billion, times e to the r times t. Well, how much time has passed from 2011 to 2021? Well, that would be 10 years, right? So you'd multiply by 10. This whole thing I'm just going to plug into my calculator now. I've got 7 e to the natural log of 7.09 over 7 times 10. Right? So 7 times e to the natural log of 7.07 times 10 is about 7.73 billion, right? Billion. That's how many people we would expect to be on Earth in 2021. Actually, I think there's more than that, right? I think we're over 8 billion right now. So I should update this problem, especially since 2021 is next year. It's 6 months away. Okay, but that was 37. And then 39 and 41, I think they're both half-life problems in some sense, right? So 39 says iodine 131, a radioactive substance that is effective in locating brain tumors, has a half-life of only 8 days. The hospital purchased 20 grams of the substance but had to wait 5 days before it could be used. How much of the substance was left? Well, I don't know how all of this works, but I would assume that they would have a way to prevent it from decaying until they actually use it, right? but apparently that's not what the problem wants us to assume. The problem wants us to assume that, hey, this thing is going to just continually decay and there's nothing you can do to stop it from decaying. Its half-life is 8 days. That's not the same thing as its decay rate, though, right? What that tells us is that it takes 8 days for half of the substance to disappear. So if we're starting with 20 grams, then after 8 days there would be 10 grams left. And after 16 days there would be 5 grams left, and so forth. The question is, if we waited 5 days to use it, how much is going to be left after 5 days? In order to figure that out, we can't really figure that out with half-lives. So what we have to do is find the decay rate. So we're going to find the decay rate. Again, we're going to use the formula P equals e to the RT. Oh, actually, we don't even need to do that. I forgot. I gave you a little shortcut for this kind of thing, right? Because I told you the half-life, h equals negative ln2 over r. So actually, I'm just going to say that. H equals negative ln2 over r. Our half-life in this problem, our half-life is 8 days. So I'm going to say 8 equals negative ln2 over decay rate, right? In other words, 8, or I guess I would multiply both sides by r and then divide by 8. So I say r equals negative ln2 over 8. That's the decay rate. Now that I have the decay rate, I can say, all right, so how much is going to be in there? I'm going to use this formula to make my prediction, right? So what's the final amount going to be? If the initial amount was 20 grams, my decay rate is negative ln2 over 8. And it's decaying for 5 days before I use it. So this thing you just plug into your calculator. I'm not sure what you're going to get, but that's how you would do number 39. 41, I'm sure, is kind of similar to that. It says tritium? Tritium? I don't know. It's been a long time since I've taken chemistry. I should probably take chemistry. Take a chemistry class and brush up. Anyway, tritium, I don't know, is used in nuclear weapons to increase their power. It decays at a rate of 5.5% per year. Calculate the half-life of tritium. Oh, this is actually even easier, right? It's giving you the decay rate, 5.5%, and it's just asking for the half-life. So if you know the decay rate, so if you know the decay rate, R, 41, so if you know that the decay rate, R, is 5.5%, as a decimal that would be 0.055. So the half-life, H, is just negative ln2 over R, in this case 0.055, and that's all there is to it. Pop that into your calculator and boom, you've got the half-life. So that's it for 41, and I think that does it for the questions that you had from this material. So again, I apologize for not being able to do this through a Zoom meeting so that you could ask questions and stuff as we went along, but until I get my internet fixed, I think this is what I'm going to have to do. I should have it fixed tomorrow. We'll see.